Hello, ladies and gentlemen. It's my pleasure to welcome us to continuation of our workshop on intermediate data analysis. Today, we'll be considering multiple regression analysis. Multiple regression analysis. Let us set our working directory straight away. So we are using the folder intermediate R as our directory. So let's import the data set. So we are still using fdat. Fdat data. All right, import. Okay. Okay. Multiple regression analysis. So we have import the data sets. We have done that, but it's good to remind ourselves. So the first thing we want to do is to regress sales as the dependent variable. Against label capital and material as the independent variable. All right. So let's start with linear function. So linear model. So let's call it linear equals, the function is lm, and we have sales as a function of that approximation sign, label plus capital plus materials. Well, let's move this portion towards the right so that we can see what we are typing. Then data equals fdat. Good. So let's get the summary. linear. Right. All right. So now we have our results. So let's try to attempt some kinds of interpretation. The adjusted R square is 0.96. The adjusted R square is the coefficient of determination, and that is showing that about 96% variation in the dependent variable, in this case sales, can be attributed to changes in labor capital and materials. So the explained variation is very high. So the coefficient of determination is high. The F statistics defining the overall significance of the model also is all right. Because if you look at the F statistics, that's about 691, and the p-value is 0.00, which means the F statistics is highly significant, even at 1%. Then let's look at interpretation of the coefficients. Let's pick labor, for instance. If you look at the coefficients, that's about 58,700. This is showing us that a unit increase, it is positive. We have to first look at the sign. So a unit increase in labor will cause about 58,700 increase in sales. So sales will increase by about 58,700 if you employ one more unit of labor. That is what this is actually telling us. Now, if you pick capital, capital is negative. That's about 0.061. And this is showing us that a unit increase in capital, for instance, will cause decline in sales by the estimate we have here. This is about minus 0.061. So then you have just be mindful of the unit of measurement. For instance, if labor here is measured as number of employee. So if I increase employment by 1 unit, that is, if I employ one more person, then my sales is measured in naira, we increase by 58,700 naira. The capital also is measured in naira, so which implies that if I inject 1 naira, if I inject 1 naira into the business, then my sales will decline by about 0.061 naira. Yeah, if you look at materials, so materials also is measured in naira, but this is positive. So, but that's 0.018. So a unit increase, or let's say a naira increase now, since we already know the unit, a naira increase in the materials, that's cost of intermediate inputs. We increase my sales by 0.018 naira. So you have to consider the signs, the magnitude. That's very, very important. But before you do that, ensure that you consider the significance of the variables. And you can see that looking at the p-values. So if you look at the p-values, for instance, all of them are highly significant, as significant at 1% probability level. So that's how to interpret the linear function. So let's try another function. Let's say we're looking at semi-log function, semi-log model. So for semi-log model, so let's call it semi_log equals lm. So we log the dependent variable sales, then we have labor plus capital plus materials, comma. Then you have data equals f that. So let's run it. And summary. Semi_log. No, this cannot be capital. All right. Let's run it. I think it's capital. Semi-log. Okay. Oh, sorry, it's f that. All right. So let's look at the results. So in this case also, the p-value shows that the independent variables are significant. But let's go back and look at the adjusted R squared. The adjusted R squared compared to the linear model is very low. In this case, it's 24%, indicating that 24% variation in sales can be attributed to changes in labor, capital, and materials. So, which means labor, capital, materials are contributing just about 24% variation in in the sales, which is the dependent variable in this instance. Yeah, if you look at the statistics, it's 87.9. That is talking of the overall significance of the model, and the p-value also is highly significant, even at 1% probability level. Let's go to the coefficients. So if you look at the coefficient of labor, it's positive. It's about 0.0031. To interpret this, please, you have to bear in mind that the dependent variable is in logarithmic form. It's in log form. So this is the way to interpret it. Label is still a linear form. So you will say a unit is still a unit for labor. A unit increase in labor will lead to 0. This is 0.031. Multiply it by 100, so that would be 0.3%. The same thing will lead to about 0.31% increase in sales. So that's the way to interpret it. Here you have increase in labor by 1 unit. We know that our labor is number of employee. So if I increase the number of employee by 1 person, then sales will increase now in percentage because we brought it in terms of log. And by what percentage? This percentage. This is 0.3%. That is, you multiply this 0.0031 by 100. I hope it's super clear. Yeah, that is it. So we can pick capital, the coefficient is very, very small. It's 0.000000. This tends to the power minus 9. But it's positive all the same. So, and by way of interpretation, though the percentage increase in sales is very small, that's 0.000000 whatever to 1. But all the same, if you inject 1 naira capital, capital is the cost of building and machinery. That is the capital. The book value, is the book value for building and machinery. That is what is used as capital. So, which means if the book value increase by a unit, then the sales also will increase, but by very small magnitude, which is 0.00000. That's up to 9 zeros, then 2, 1. Yeah. But if you look at materials, the coefficient is negative, which means that if cost of intermediate inputs increase by a unit, which is naira, let's say by 1 naira, then the percentage, don't forget it's percentage sales will decline by, it's very small, that's 0.0000, but it's minus 2.57 multiplied by 10 to the power minus 10. Yeah. So I hope that is easy to understand. Let's move to the third. We have log model. Now this is a situation whereby both dependent and independent variables are in log form. So let's have log underscore log equals, so we have lm, so we have log sales as a function of log labor plus log capital plus log material then data equals f that. So let's run this. All right. So summary, log run. All right. So let's check the results. So in this case, all the variables are statistically significant too. Yeah, at 5%. Yeah, that's all right. So let's consider the adjusted R square. In this case, it's 0.88. So that's showing that about 88% variation in sales can be attributed to labor capital and materials in log form now. Don't forget that. So, and that is relatively very high. And if you look at the p-value, the F statistics, I'm sorry, that's about 204. And the p-value is 0.000. That is 2 multiplied by 10 raised to the power minus 16. So the overall significance of the model described by F statistics shows that the model is a very good fit. So, and the p-value is okay. So by way of, let us now try to interpret the coefficients. Yeah, let's pick labor. Yeah, in this situation now, we have all the variables to be positively correlated with the dependent variable, which is the log of sales. Don't forget that. So the coefficient of labor is 0.85. So don't forget the dependent variable is in log form, the independent also is in log form. So you have to interpret the relationship in terms of percentage change. So the To interpret 0.85, for instance, we say that 1% change in label, 1% change in label will cause about 0.85% change in sales. Yeah, that is how to interpret the coefficients. For capital, for instance, a 1% increase, that is increase to is positive, in book value of machinery and building will cause about 2%, 0.02, about 2% increase in sales. If you look at materials, which is cost of intermediate inputs, so if the cost of intermediate input is increased by ₦1, then sales will increase by about 27.2%. We increased by about 27.2%. Yeah. So take note. When you are using log, you interpret in terms of percentage changes both ways. For semi-log, you interpret the independent variable in terms of unit increase, but leading to percentage change in the dependent variable. For linear model, you interpret in terms of unit changes, both sides, dependent and independent variable. So a unit change in the independent will actually lead to the estimate. That is, the estimate is interpreted in terms of unit change in the dependent variable. So it's unit for linear, unit percent for semi-log, percent for log. I think that is a very simple way to to remember the interpretation. Yeah. So the next thing we want to do is to present all the results in one table, so in a neat form. So for that, we need a library. Sorry, okay, so as presenting the results in a neat table. So we have library, Stargazer. All right, so Stargazer. So the first is linear. The second is semi-log. The third is log. Type HTML. Out. So let's call it let's say mreg dot doc. Yeah. So let's run it. So beautiful. So let's look at the results. Let's double click here. We call it mreg m. Okay, this is it here. So let's open it. So this is the results. This is all the results at once. Yeah, so these are the three different models. So the first is the linear, the second is the semi-log, and the third one is the log. Good. Yeah. But in terms of how reasonable the results are, if you look at the results, you may want to look at the residual standard error. So the one with the least residual standard error is actually the log, which is that's 0.443. And if you look at the coefficient also, if you look at the coefficient for linear function, the values are extremely very high, but compared to when we have compared to the results for the logarithm function. So to me, it will be better for to proceed with the log function. So just be guided and know what you are trying to do in explaining the reason for whatever you have chosen, upon which you want to base your policy recommendation. So for me, that will base my policy recommendation on model 3. Yeah. In fact, by considering the R squared, there is no basis for considering the second model, which is the semi-log. Yeah. So going forward, I think we should just focus on the log, because we still have to make some adjustments. So let's go back to our studio. All right, so now we want to look at regression with categorical independent variables. Good. So if you look at the variables that we have fitted, we have not included any categorical variable. But let's say we want to include industry, for instance. So we want to see whether industry, which would be uh, a kind of fixed effect, industry fixed effect. We want to see whether it's going to influence sales one way or the other. That is, whether the type of industry will actually influence sales. In this case, industry will be brought into the model as dummies because it's actually qualitative variables. So it's always approximated as dummy variables. So we have three types of industry in the model. We have food, we have wood, then we have garments. So the starting point is you have to be sure because you have to make one of them the reference group because since it's 1-0, you cannot include all the three because if you include all the three, the model will not run. Yeah, it's going to give us a singular matrix. So you have to decide what are you using as the reference group. You have to provide the reason why you've chosen that as reference group. For instance, am I trying to compare food with others, or I want to compare others with food, or I want to compare others with garments, and so on and so forth. So because anyone that you have chosen as a reference group will determine the way you interpret, because the interpretation must be based on the difference between the variable and the baseline. Yeah, so please. So let's start by making food as okay. First, try to get the different categories. So we have table f that dollar industry. So let's run this. So you can see we have food, garment, wood, and please be mindful of the spelling because as we already know, R is case sensitive. All right. So let us use food as so we have f that dollar industry equals with f that comma. So we have factor industry comma. So we have levels. So and see this where you have to pay attention to which one you want to use as the reference group. Anyone you want to use as the reference group must be the first to be typed, must be the first one, the first category. So in this case, if I want food, I will put food as the first. If it's garment, I will put garment as first. If it's wood, I'll put wood as first. That is how to make it the reference group. So food, then I will now bring the other ones, garments, and wood. So that's how to define the reference group. Yeah, good. So I've made food as the reference group. So by the time I run the regression, you will see that food will be omitted, so that I'll be explaining the coefficient of garments on wood in reference to food. That is how to handle it. So let us run the regression. Let me call this. I want to proceed with log. So let me call that one log 1. So equals to so to save time, let me copy the previous log function. Okay, let me copy everything here. So copy. All right, so this paste. So plus industry. Yeah. So this would be log 1. This would be log 1. So let's run everything. Beautiful. So let's look at the results. Now, if you look at the results, you can see that wood industry, the coefficient of wood industry is 0.1119, is significant at 5% level. That's fantastic. So that is the one that we will try to interpret. So let us interpret this 0.119. All the coefficients are positive in terms of sign. So which means being in the wood industry, we increase sales by 11.19. No, that's multiplied by 100, 11.19% relative to food industry. Take note of that, because whatever you are defining, whatever you are explaining must take into consideration the reference group. So let me take that again. Being in the wood industry, we increase sales by 11.19% relative to food industry. That is, compared to food industry, being in the wood industry, we actually increase sales by 11.19%. I think that is very clear to understand. So, yeah. And that takes us to regression with interaction terms. Yeah, regression with interaction terms. So we may want to interact our label. No, don't forget that our label is in log form with industry, and see whether the interaction between label and industry will have meaningful or significant effects on sales. So again, let's copy what we have here. Copy, paste. So we have plus. In this case now we have industry. You see multiply by log labor. Yeah. So let's change this to 2. This to 2. So run. Right. Yeah, beautiful. So now, if you look at the results, okay, let me, so that we can see the results clearly. So let me run it again. Okay. Yeah, okay, this is fine now. If you look at the results, you will see that labor, the coefficient of labor, a log of labor is 0.8956 and highly significant. And the coefficient of industry, let's go back. The coefficient of interaction of garments and industry is insignificant. But if you look at labor and industry, the coefficient is minus 0.09523. And if you look at industry, garment industry wood, if you look at that in the previous example, we discovered that the coefficient of wood industry is statistically significant, positive. So let us now look at how to interpret this interaction term, which is the log of labor and wood industry. Yeah. For wood industry, that is the way to interpret it. A 1% increase in labor will increase sales by, now we will add, this is minus 0.09523. We will add that one to 0.89560. Or in other words, since that is negative, we have to subtract that from this. Yeah. So, and if we subtract, we'll be getting something like 0.8, I think 0.00 something. So, which means that the influence of labor actually decline because of its interaction with wood, but in the wood industry. So, which means labor has a weaker effect in the wood industry sales compared to that of food. Don't forget, you can say that the result for food is not coming up because that is the reference group. So you still have to keep in mind the reference group. So labor has a weaker effect on wood industry, on sales from wood industry compared to sales from food industry. So that is the overall explanation, because actually it reduces the effect of labor. The effect of labor originally was 0.89, so and so on. But by the time it's interacted with labor, just you can see that the interaction time is negative 0.095. So subtract that from the coefficient. So it's going to give us around 0.8. So please bear that in mind. So you already know how to interpret R squared and the F statistics. Yeah. So there is something we quickly want to, if you look at these results, let's look at the results. If you look at it clearly, yeah, as a reminder, you don't bother yourself interpreting insignificant coefficients. You can see that the coefficient of the interaction between labor and garment industry is not significant. So you don't need to worry yourself interpreting that. Take note of that. All right. So let us move our log1 and log2. Let's present it in the table. So copy this here. Paste. So here I have log1. Then I don't need this. log2. So let's say this is mreg1. Run. Beautiful. So let's look at the results. Mreg. Sorry. So mreg. So this mreg1. So let's open it. Yeah, beautiful. So now if you look at these results, you will see that the values in the brackets are the standard error. You may wish to use T instead of standard error. Yeah. If you desire to use T, then you have to make a small change in the source code. Notice the beauty of R. You can actually look at the source code for any package. So we'll go to the source code for Stargazer, then we make small change, and instead of having the standard error, then you can have it as T. So let's make that small change. So to make such change, so let's do this. Excuse me. So reporting T value instead of standard error. Yeah. So you say trace Stargazer. So you have, so you look for stargazer.wrap, then comma, edit equals to true. That is, I want to edit the source code. So, sorry, let me move this a little. So run. All right, so let's look. I think the source code should be around where you want to make changes. 71. Yeah, it should be 7104 something. All right, so now you can see um oh, it's already formatted. So this is 7105. So it's the bracket is open and close here. But in some, you will see it's not the it, it's not opening the bracket and closing. It's going to say T equals. Then this one will not have the bracket. So in that wise, you have to make the changes. But in this case, I think it's okay. Maybe I've done it sometimes. So save. So the moment you have done that, then to have your results in t-value form, so you have to say report. So and the report, that's in quotes here. The report will be VC multiplied by T. This will be comma. So let's change this to mrep2. So let's run this. Beautiful. So let's come here. So and so mrec2, now this mrec2. So open. So you can now see that here we have the t values this is the first one. We have the t values instead of the standard error. Yeah. So these are the t values. Beautiful. Now don't forget you can change your table design the way you like. Yeah, it's all right. All right, so I think now we want to go for assumption diagnostics. So let's move to assumptions diagnostic. So we need library car. So library car. So let's pick it here. So library car. And let's start with normality assumption. So normality assumption. So normality assumption. So for normality assumption, we want to be sure that the residual of our model is normally distributed so that the assumption of normality is not violated. So one way to do that, we can actually plot what is called QQ plots. So let's start with QQ plot approach. So we have QQ plots. It's in car package. So let's use it for log 2. Yeah, so let's run it. Yeah. So our interest is whether the point actually fall on on the line. And if you look at this, most of those points actually fall on that line, indicating that the residual is actually normally distributed. So, but you may wish to use Shapiro test. So this is Shapiro, so you type Shapiro.test log 2. So run. Oh, sorry, there is log is for the residuals. It's for the residuals. Just all right. So it should give us a result now. So beautiful. So now what you are looking for, if you look at the p-value, for instance, is already greater than 0.05. So which means the null hypothesis of normality of the residuals is not actually violated. So you cannot reject the null hypothesis of normality of the residuals. So just check for the p-values. That's a very fast way of doing it. Okay, let me move here. So the next thing is heteroscedasticity test. So heteroscedasticity tests. So in this case, we want to know whether the variance of the residual is constant or not constant. So we use what is called non-constant variance test, that is NCW tests. So in that wise, we have NCW, so NCV, sorry, not constant, NCV testing car, and then log 2. Now you can use it for any of the models. I just pick log 2 being the last model that we estimate. But usually the approach is you use it for anyway, you can use it for the model and compare their results. Yeah. To guide you in your final choice of the model for policy implications or policy recommendations. So if you look at the result also, just look for the p-value. This is already greater than 0.05, which means that the assumptions of homoscedasticity, the null hypothesis of homoscedasticities cannot be rejected. So there is no problem of heteroscedasticity here. Yeah. Multicollinearity. So let's multicollinearity. Sorry. So for multicollinearity, let's say method 1. So for the first method, we'll be using the VIF, that's variance. So let me write it in front. So we are using variance inflation factor method. So just type VIF, then we have log underscore log 2. So run it. All right. So, hey, I want to see. So let me run it again. Oh, sorry. Okay. Now if you look at the values, um, yeah, if you look at the values, you have just focus your attention on the direct input, labor capital, materials, because uh, the industrial and the interaction, they are shift variables. So in that wise, just check whether the values are greater than 5. So anyone that is greater than 5 suggests problems of multicollinearity. But in this case, we can conveniently say that multicollinearity is not a serious problem. So, and let's test for outlier. So we have outlier tests. So say outlier tests. So let's log 2. So run it. Yeah, but in this case now, you can see that this observation 813, look at the p-value is less than 0.05. It's an outlier. In fact, if you look at the graph for the QQ plot, you can see it as an outlier. 813 is already there. So one thing you can do, you can go back to your data set and check for that firm. Look at that observation and see maybe something is wrong somewhere, because sometimes you may just need some kind of cleaning. Maybe you have duplicated values, or maybe values entered in error. But if it's not in error, no. Out of 825 observations, if I just having one, I can actually delete it to reduce the negative effects. All right. So let's move to test for influential observation. It's another way of trying to bring out the outlier. So test for influential observations. So in this case, we have what is called influence plots. So you have influence plots, so influence plots, sync package. Yes, sorry, it's not coming up. Influence plots, yeah. So log underscore log 2. So let's run it. Yeah, fantastic. So you can see the cook distance plot. So you can see plot of the residual against the cook distance. So in this case, we are against the fitted values, then calculating the cook distance. So we can see it's not just 813, so we have other 5 variables that could be described as influential observations. So we have observation 696, 699, 704, 813, and 817. We may want to go back to the data set and look at those observations to actually find out what's going on. Yeah, so and Yeah, we may also try to look at what is called residual plots. Say residual plots. So if you want to do that, we have residual plots. Let's say log underscore log 2. So residual plots. So let's run it and find out what's going on. So you can see clearly, residual plot is the plot of the residual against the fitted value. So, and it's showing us quite a lot. So in terms of linearity absorption, in terms of um, heteroscedasticity, and quite a lot of information actually. So, but I think it's better to actually consider so many of these assumption diagnostics and be sure that you are reporting a model that's fairly reasonable. That is the most important thing. So you can do that for all the other models that you feel you may want to report and compare your results. All right, so that takes us to Logit, Probit and Logit model. Probit and Logit models. We use Logit, Probit and Logit model when we are dealing with binary dependent variables. That is, when our dependent variables are measured in binary forms, such as yes, no. Let's say I want maybe choice of maybe adoption. Let's say you want to adopt one innovation. So you adopt yes, you do not adopt no. Maybe in terms of votes, okay, you vote and you don't vote, one of things. Employed, not employed, participated in labor force, not participating in labor force. As long as you can measure whatever you want to consider in terms of um, dichotomous, if it's dichotomous variable, then you are good to go if you want to apply Probit on the Logit model. So let's fix idea. Let's look at drivers of labor force participation, LFP, labor force participation. So let's import the data set. So let's file, I think it's LFP. It's our LFP data. LFP, IJKL. Yeah, this LFP data. So import. All right, so that's good. So import. So and let's go back to sorry. Yeah, this is so to remind us of our color names or names, LFP data. So this run it. So it's a kind of labor force participation data. K is keyed under 5. K618 is keyed between the age of 6 and 18. Age is age measured in years. WC is I think whether the wife is earning income, yes or no. Whether the husband, AC. So times the wages, the log of wages is WT, then INC is the income. All right, so let us look at the categories because your dependent variable must not have more than 2 categories. So let's check it first. So we have table. LFP data dollar LFP, so run. So we have two categories with no yes. So it's advisable that you actually transform the variable into 1, 0, that is 1 for yes, since we are looking at drivers of labor force participation, and no will be 0. So let's try to do that. So we have LFP data equals to LFP data percent greater percent. So we have mutate LFP equals if else LFP equals yes. Then if it's yes, 1. If it's not yes, 0. Let's have this so that we can see clearly what we are trying to do. All right. Good. So let's run it. Beautiful. So try the table again. Instead of no yes, now it's going to be 0. Yeah, beautiful. So we now have 0, 1. Yeah. So now we can run the Probit model. So Probit model. So for the Probit model, let's call it Probit underscore model equals, in this case, is GLM. Don't forget it when you are dealing with quantitative variables and you want to run the ordinary least square model is LM. But for this discrete choice model is GLM. So our dependent variable is LFP. Then let's say function of. So let's bring out the variable age plus K5 plus K618 plus WC plus HC plus K618 plus INC, comma, then data equals LFP data. So then comma, then you have family equals binomial. Then you define the link equals Probit. That's all. Good. So let's run it from 77 to 79. Run. Good. So we have summary. Probit model. All right, so let us look at the results. Yeah. So if you look at the estimates we have here are the odd ratios. Take note, they are the odd ratios. So don't forget the odd ratios is actually the probability of success divided by probability of failure. In our situation, let us not forget that our interest is the probability of participating in the labor force or not. So each of these values represent the odd. So if you look at age, for instance, the coefficient can be interpreted in terms of the odd. So increase in age reduces the odd of participating in labor force. So you are less likely going to participate in labor force as you become older. That is just what this is telling us. So that is how to go about interpreting it in terms of odd ratio. Also, having young kids, maybe 0 to 5 years, also reduces the odd of participating in labor force. So, which means that you are less likely to participate in labor force if you have kids between the age of 0 and 5. The same apply to having kids between the age of 6 and 18, and so on and so forth. So, yeah. But if the wife is earning income, that's positive. So the odd of participating in labor force actually increases. So you are more likely to participate. So it's straightforward to interpret in terms of odd ratio. But we can proceed further and actually interpret in terms of a small change leading to changes in the probability. So if that is what we want, then we have to calculate the marginal values. So marginal values for Probit model. So if you want to calculate the marginal values, you will need margins, library margins, yeah, margins. So run it. So and let's say Probit MV now marginal value equals margins. Sorry, margins Probit model. Probit model. Yeah, so run it. So then you have the summary, Probit MV. So run. So you can actually interpret this in terms of marginal values. So if you look at the age, for instance, now, you can now say a small change in age. That is, let's say age increased by just 1 year. The probability, this exact probability now. So the probability of participating in labor force will decline by is multiplied by 100, that's 1.3%. So it is clearer in terms of interpretation. So don't forget that if the husband is earning income, for instance, now the probability of participating in labor force will increase by about 2.28%. This is clearer. So you can actually interpret this directly in terms of probability. That is the beauty. All right, another thing we can do, we can have what is called cplot. So let's say if you want to use cplot, for instance, you say cplot for the model, Probit model, comma. Then we can have it for maybe a variable, let's say age. So let's drag this here so that we can see the graph. Run. So beautiful. So you can actually see, it's always clearer using graph. So this is the predicted probability, and we can see it declining as age increases. So showing the inverse relationship clearly. So you can do that for any of the variables. So that is Probit. So and that takes us to the last thing we want to do, which is the Logit model. Logit model. Logit model. Logit model. So for Logit model, no, it's the same process. Just come here, then copy, then so you have paste. So just change this to Logit. Change this to Logit. And this is the only thing that we change is the link. So just change the link here to Logit. Super clear, super simple. Hey, don't forget this will be Logit. So run this, and get your results. So, and we follow the same procedure in terms of, so let's just copy 84 to 86 and make some little changes. Copy. Paste. So we have, so let's say Logit, sorry, Logit, 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 Logit. So you can have the marginal, these are the marginal values, almost the same. And then in terms of the cplots, yeah, yeah. So then in terms of model comparison, because we want to model comparison, that is, I want to compare my Logit and my. So what you need to do, we have library, we have rcompanion. So then you have what is called nagelkerke. So nagelkerke. So do it for Probit model. So you will get some estimates. So look at all the estimates here, so many of them actually. So you have the log likelihood, you have the cock smear, you have the pseudo R, you have a lot of them. So you do the same for nagelkerke. So you do it also for Logit model, Logit model. So and you compare the estimates. So let's look at the pseudo R, for instance. The pseudo R here for let's pick McFadden 0.10 for Logit. Let's see the result for Probit. Yeah, I think this is 0.1039, while this is 0.1044. So which means for the Logit is a little bit higher. So which means it's a better fit, at least slightly better, and so on. So you can compare some of those estimates. You can look at the log likelihood and so on. For log likelihood, you have to consider the one with uh, smaller magnitude. Yeah. So these are various things to do if we are comparing the two. So I think the next class we are going to look at multinomial logics as well as panel data regression. So thank you. You are mostly welcome. See you again in the next class.